All right, this is the last lecture of this unit, which means next class is a review day. There'll be nothing new introduced. Maybe we'll go over specific types of problems that you aren't familiar with, but in terms of concepts, there will be nothing new. We will go over quizzes. And if you have any questions from all the quizzes that you've taken, including the one you just took, we will answer any questions we have. We will take a quiz on the section that you'll learn today. And you'll get your review packet, which will not be collected, but it'll be extra practice problems you can do. And then that'll get you ready for your test next Tuesday. So your first test is next Tuesday. This last lesson for this unit is also on finding limits analytically. However, it is with trig functions being involved rather than just x squared, square root of x's. So what I wanted you to do is find these three limits. So let's find this first one. What did we find the limit as x approaches 0 of sine x over x was? Did you get it, Ms. Dawson?
1.
Yeah, it's 1. If I look at the graph, it's an interesting graph. If I look at 0 when x is 0, there's no defined value. However, so that means there's a hole. However, the function is approaching this value, which looks to be 1 as we get closer to 0. If I plug in 0.001, once I press trace, I can see that my y value is approaching 1. Cool. What about the other two? Let's find the other two. Ms. Gross, what did you get for the second one? X over sine x. 1 is correct as well. And what about 1 minus cos x over x? Anybody get that? Ms. Bench, did you get that one? 0 is correct. Okay? There's no other way we can find these three limits. We can't think of manipulating this to simplify this x in the bottom. Nothing happens. Instead, we have to find it numerically. But what's special about these limits is that we're going to use them to help us find other limits with trig functions. So we need to commit, especially this one, to memory. We need to know from now on that the limit as x approaches 0 of sine x over x is 1. We'll call them trig limits. And we'll call them tough trig limits. Tough trig limits. Okay. But of course, we have to remember there are easy trig limits. The ones that you did for homework. Like the following, the limit as x approaches 0 of sine of x. What do you do for this one, Mr. Bolner? You did them for your homework. What's the first thing we should try to do when we're trying to find a limit? Yeah, just plug in 0 into the function to see if the function exists at 0. If it does, that's your limit. This is 0. That's a number. It's not undefined. It's just 0. Same thing for secant. We want to find the limit as x approaches pi over 4 for secant. Plug in pi over 4. If you get a value, that's going to be your limit. So let's do secant of pi over 4. Cosine of pi over 4 is root 2 over 2. Secant would be 2 over root 2. Do you have to rationalize? No, not unless this is a multiple choice problem. Yeah. If it is multiple choice, you would need to know that this simplifies to just be root 2. Sorry for being scrunched. You need to know there will be lots of multiple choice questions on every test. AP exam is split half multiple choice, half free response. So it's important to know how to rationalize. Yep. But of course, these are the easy ones. There will be other ones that we're going to be doing that aren't going to be as easy. Okay, these. I'm not going to be able to just plug in 0 into 1 minus cosine x divided by x sine x. To do those, we're going to need 2 things. We're going to first need this limit that we've committed to memory. We'll also need these properties that we're going to use, as well as some trig identity properties that we're going to use. So this is simple. I kind of talked about them last class, just briefly, and you had a couple of homework problems that are kind of easy. You'll see a couple of problems like that on your test, maybe 1, maybe 2. But I changed it to a dot, so it's multiplication. If you have the limit as x approaches some value of 2 different functions being multiplied together, you just find the limit of both functions separately and multiply those together. Quick example we can do, the limit as x approaches c of f of x, let's say as x approaches 3 of f of x. If that's equal to 5, this is an example, and the limit as x approaches 3 of g of x is 2. If I asked you to find the limit as x approaches 3 of f of x times g of x, all at once, all you would do is say, well, this limit is 5, this limit is 2, this limit therefore is 10. Okay, pretty simple. It's kind of the same thing if we have a constant times a function. We could take this constant out and then just multiply it by the limit of the function. Using, say, this as an example, I could say find the limit as x approaches 3 of 4 g of x. Well, you know the limit as x approaches 3 of g of x is 2. I would just take this 2, multiply it by this 4, you get 8. Simple, right? Makes sense. You just kind of take these numbers and you plug them in. This is 5, this is 2. This is 2 that I use, times 4 is 8. Okay? Other things you need to remind ourselves of are trig identities. We will be using these to help us rewrite some of our limits. Cosecant, we remember, is 1 over sine. Secant, 1 over cosine. Cotangent is 1 over tangent. Tangent can be written as sine over cosine. And since tangent can be written as sine over cosine, cotangent can be written as cosine over sine. Okay, now we got this one, sine squared of x plus cosine squared of x. What does that equal? Is that you, Mr. Magnella? Yes, that's correct. This is 1. Now, great thing about this one is we can manipulate this one to get any other one that we kind of have to know. Like, do you remember any of the other ones where it's like tangent squared plus something equals something else. Do you guys remember those from last year? No, you don't remember any of them, right? But you remember sine squared plus cosine squared equals 1, at least, right? Well, watch. We can do a lot of stuff with this one to get all the other ones that you might have forgotten. Oops. First thing we could do is manipulate this one by subtracting. Where was I? Here. So if I wanted to, I could subtract like cosine squared, or I could subtract sine squared to make a new identity like sine squared is equal to 1 minus cosine squared. And you could do the same thing by subtracting sine squared. Okay, so that's the first guy. Second guy, I could take all three of these guys and divide them by, say, sine squared. Now, what's sine squared over sine squared? It's just 1. What's cosine squared over sine squared? Cotangent, exactly. Cosine over sine is cotangent. Well, if I have cosine squared over sine squared, that'd be cotangent squared. And then what would be 1 over sine squared? Cosecant squared. 1 over sine is the same as cosecant. Well, 1 over sine squared is cosecant squared. Look at that. You don't remember that one. You probably were told to memorize that one. However, what you didn't know, that you could have just generated this one yourself. And we could do the same thing by dividing everything by cosine squared. And when you do that, you get tangent squared. That's sine squared over cosine squared. Plus 1 is equal to secant squared. Who knew it was that easy to generate those? All right. So now that we have all these trig identity reminders, we reminded ourselves of certain trig, certain limit properties, and we have this guy committed to memory, we're ready to go. Tough trig limits. The key to tough trig limits is to remember this guy. That the limit as x approaches 0 of sine x over x is equal to 1. This is kind of going to be our helper. What do I mean by that being our helper? Well, let's take this first limit as x approaches 0. If I plugged in 0 everywhere, I'd get an undefined value. Not good. But using my limit properties, I see I have a constant times sine x over x. I could pull that constant out if I wanted to. Now I have a constant 3 times the limit as x approaches 0 of sine x over x. I know this limit is 1. So this turns into 3 times 1, which is 3. Simple. Now, what you'll probably do for your homework is instead of writing this step, you'll just look right here. And you'll say, okay, I know this limit is 1, multiply it by 3, 3. Right? Mr. Magnella? That would be different. We will do that later. Good question. Sine of 3x over x will be different. The answer will be the same, however, but it's a different process. Okay, next problem. Limit as t approaches 0, this should all be t's of t cubed plus 9 sine t times 1 over t. To do this, we need to think about certain properties of multiplication and multiplying fractions. Think of a simple example of like 3 times 4 times a half. Well, since we have multiplication, I can do this in any order I want. I could say this is equivalent to 3 over 2 times 4. I can say, well, that's also the same as 3 times 4 over 2. 3 times 4 is 12 times a half. That's 6, right? 3 halves times 4 would give you 12 halves, which is 6. 3 times 4 halves, or 3 times 2, that would give you 6. Which means you could take this. Also, you could even go 3 times 4 all divided by 2. Which means you could take this piece and you could kind of move it wherever you want to. Doesn't really matter. These are all the same. What I mean by that is that in this limit, what I can do is take this 1 over t and just put it underneath sine t. And we have t cubed plus 9. We'll keep that by itself. And then we'll have sine of t over t. Well, again, we have two functions that we're trying to find the limit of. We can separate this into two different limits and multiply them together. The limit as t approaches 0 of this first guy, t cubed plus 9, times the limit as t approaches 0 of the second guy. You know that this is just 1. You know that for something like this, I can just plug in 0 in for t, and I get the square root of 9. That's 3. Well, this limit is 3. Will you have to do this step when you do your homework? No, you will not. Instead, you can just get it to look like this, and then you can say, all right, this is simple. This limit, since t is approaching 0, is 1. This limit, I plug in 0, I get root 9. That's 3. You guys can go straight to just your answer, which is 3. Okay. Let's do another one. This will involve our knowledge of some trig identities. So the limit as x approaches 0 of tan x over x. We're still going to use my helper. We will still use this limit to help. I still cannot plug in 0 into tan x over x. Because I get an undefined value. But I'm still will use this limit that I discovered, sine x over x, as x approaches 0 is 1. How do you think I can use this to help? What do we think, Mr. Brunn?
Change tangent into sine over cosine.
Exactly. Let's rewrite tangent into sine over cosine. Then instead of dividing sine over cosine by x, what can we do?
Take cosine out. 1 over cosine out.
Yeah, we could take the 1 over cosine out. We can move the x to be times 1 over x. Maybe that's easier. Now, just like the last thing, if I have something like 3 times 4, or 3 halves times 4 thirds, let's say 4 fifths, I can move around any of these numbers, and I'd still have the same thing. I can make this 3 fifths times 4 halves. I would still get 12 tenths. Here, I can turn this into sine of x over x, and then times 1 over cosine x. I can kind of move things so that we have what we want to see that we can work with. All of a sudden, x pops over here, cosine will pop over here. We know that this limit, I won't show that extra step anymore. I'll kind of do what you guys will do, where you can say, okay, this limit as x approaches 0, this is 1, times this limit. Well, I'll plug in 0 into cosine. The cosine of 0 is 1. This is 1 times 1 over 1, which is 1. Okay, let's do something like this. I'll do quickly for you just to show you if you have something like sine squared. It's important to know that sine squared is the same as sine of x quantity squared. What I will do here is just rewrite sine twice. And now I have an x underneath it. Well, I have kind of one big fraction. I should know that I can split this into two smaller fractions being multiplied by each other. Sine x times sine x over x is the same as sine x over x times sine x over 1. Because you just multiply across, and you get sine x multiplied across times 1 would be x. Well, now this, we know the limit is 1. This guy, I would be able to plug in 0 in for x. Sine of 0 is 0. So I'd have 0 over 1, which is 0. This limit is 0. Why don't you guys try this one? You will have to use a trig identity, and then you can simplify it. Just like the other ones, we will use sine x over x to help us. Anybody get it? Ms. Karchevsky, did you get it? Okay. I'm rushing because we don't have much time because it's a club day. 1 minus cosine squared is equal to sine squared. Sine squared plus cosine squared is equal to 1. 1 minus cosine squared would be equal to sine squared. So I rewrite this as sine squared over x sine x. Then I rewrite sine squared as sine over sine. If you want to split this up into two fractions, you can, or you can immediately cross out a sign. Cancels with another sign. You just get the limit as x approaches 0 of sine x over x. Okay, a little bit tricky. Mr. Magnella.
Can you combine the bottom with sine x squared?
The bottom, no. So sine x times x is not sine x squared. It would be x sine x. So that x is being taken hostage by the sine. It cannot be penetrated by other x's. Okay, let's go to this problem. Trig functions with a constant times a variable. So, kind of like what Mr. Magnella was asking before. I'll show you how you want to do this, but you'll probably find tricks of your own as you're doing the homeworks. So let's go back to the first day of class when I asked you to figure out when the sine of 5x was equal to a half. How'd you do that, Miss Pennington? Yeah, you kind of ignore the 5. You kind of just say, well, let's figure out when the sine of some other variable is equal to 1/2, right? Not necessarily we ignored it, but we kind of did. We substituted it. We're going to do the same thing here. I'm going to kind of ignore the 3x, but not really. I'm going to substitute and replace it. I'm going to say something like a u is equal to this 3x. All right? Now, what's cool about this u is I can replace this 3x with that u. So let's start with that. I'll replace 3x with the u. However, if I have u's, I want just u's everywhere. So I don't want to put u down here, or x down here, and I don't want to put x approaches 0 down here. Okay? Let's see what I can replace x with. If I know u is equal to 3x, I can solve this for x. And all of a sudden, I discover that x is equal to u over 3, or 1/3 u. So instead of this x down here, I'm going to say we have 1/3 u. And what's great is that as x is approaching 0, 1/3 u is going to also approach 0, or just u is approaching 0. You do not need to replace this with a 1/3 u. This is u. Now, what happens? I divide by a fraction. It's the same as multiplying by the reciprocal. The 3 is here. Now, Mr. Magnella, we see we have 3 sine u over u. That limit is just 3, because this is 1 and this is 3.
I have a question.
Yeah.
So why can't you just multiply 3 times 0 and then have 0 over?
Why can't you multiply 3 times 0?
Because it's approaching, oh, that'd be the function.
Because well, yeah, the sine of 3 times that value will still be different than just the sine of the value approaching 0. You see what I'm saying? I want you guys to write this one down and then at least copy down how to do it. It's going to be the same process. Step 1. Set some different variable equal to what is ever inside your trig function. Step 2 is to solve for x. Step 3 is to substitute. What I will do is, hang on, we got club time. I will substitute extra u here. I'll substitute 2 extra u here. And then, instead of 5x, I'll have 5 times 1/2 u. Well, that's kind of like 5 halves in the denominator. I can multiply this by the reciprocal, giving me 2/5 times 4. I could separate stuff out, times sine u over u. I'm trying to find the limit as u approaches 0. I know this is 1. This would be 2/5 times 4, which is 8/5. And this is your answer. Now, what do you notice? You notice that you could take this 2 and multiply it by this 4 and divide by 5. You get the answer. You could take this 3 and kind of pull it out, and that'd be the answer. In the end, I kind of want you to find the right answer no matter what. This would be the proper mathematical way to go about doing it. So work on your homework. Use these as examples. Come in with questions if you have any. Thank you.